Step into a chilled data hall on the outskirts of Santa Barbara. At its center, a spider-shaped chandelier of gold and wires hangs inside a steel cylinder colder than deep space. This is a quantum processor. When engineers nudge its qubits, the chip tackles in minutes a calculation that would keep the world's largest supercomputer busy for days. The trick it plays has a name that sounds like science fiction. Superposition. The art of holding mutually exclusive truths at the same time. We have met echoes of this art before. Aim a beam of single electrons through two razor-thin slits and, one by one, they paint a ripple pattern on the screen behind. Each electron seems to explore both paths at once, interfering with versions of itself we can never see. Block either slit, and the pattern vanishes. Reopen it, and the waves reappear, as though reality hesitates until we force its hand. Superposition is more than a laboratory stunt. It shapes the colors of chemical bonds. Lets photosynthetic molecules hunt multiple energy routes in a trillionth of a second, and may guide the midnight migration of birds under starlight. Yet the idea collides with everyday instinct. A coin on the table is heads or tails, not both. A coffee cup sits here or there, never in a ghostly blur of possibilities. In 1935, seeking to expose the tension, Austrian physicist Erwin Schrödinger imagined a sealed box containing a cat, a single unstable atom, and a vial of poison set to shatter if that atom decays. Quantum math says the atom must hover between decayed and intact until observed. Does that put the cat in a limbo of life and death? Schrödinger offered the scenario with a wry smile, convinced such absurdity signaled a flaw in the theory. Decades of experiments have only deepened the puzzle. We can now place tiny superconducting loops into cat states, carrying electric currents clockwise and counterclockwise at once. The paradox refuses to die. Instead, it powers new machines and provokes fresh philosophies. Tonight, we will follow these overlapping drafts of reality. We will trace the double slit's whisper, walk the length of Schrödinger's box, weigh the rival explanations for what counts as a measurement, and meet the technologies already harnessing nature's indecision. By the end, you may find comfort or wonder in the thought that every sunrise begins as a superposed script, that certainty, like daylight, dawns only when we open the box of the world and look inside. Picture an electron gun, no larger than a thimble. An operator fires a single electron, just one, toward a screen the size of a playing card. Expect a tidy speck, the way a pelletniks would. Instead, after a handful of shots, pale zebra stripes appear. Bright, dark, bright, dark. It is as though each lone electron has rifled through both gates of the double slit at once, and argued with itself about where to land. Centuries of one object, one path, fall silent in the glow of those impossible bands. To be sure nothing sneaky is happening, the scientists slow the experiment to a crawl, one electron every few seconds. You could knit a scarf between arrivals, yet hour by hour the interference pattern rebuilds, crisp as before. Imagine standing on a deserted beach at dawn, tossing a single pebble left, waiting, then tossing another right. Dawn swells into noon, and somehow, the sand records two overlapping sets of footprints that dance in perfect synchrony. No wind, no tide, just a walker who seems to have strolled both halves of the shore in the same morning. There is no hidden crowd of electrons lending a wave. Each arrival is isolated, indivisible, innocent. Still, the stripes bloom. Nature, it seems, prefers to keep her options open. Perhaps someone suggests each electron really does take just one slit, and our instruments are blind. Tiny detectors, gentler than moonlight, are slipped behind the apertures. Their only task is to whisper left or right when an electron passes. The moment the detectors power on, the stripes evaporate. Two plain blotches replace them. Switch the detectors off, and the zebra returns. It is not a prank of disturbance. The detectors barely nudge the particles. Instead, the mere possibility of learning the path rewrites the landscape. Information itself bulldozes the wave of maybes into a single either-or. It is like asking a storyteller which ending is real. The alternate finale vanishes the instant the question leaves your lips. What then travels between gun and screen? Not a billiard ball, but a whisper of chance, a spread out maybe, whose peaks show where arrivals are likely and whose troughs mark the neverlands. Where two maybes overlap in step, they reinforce, bright as a choir hitting the same note. Where they meet out of step, they cancel, and darkness falls. You can think of it as water rippling from two stones. Some crests meet crests, building higher spires. Others meet troughs, flattening the pond to glass. This soft geometry of probabilities guides every electron, photon, and atom. It sketches countless routes, lets them interfere, and settles on a destination only when reality is called to the podium to read a single line. Perhaps the weirdness fades with weight. Hardly swap electrons for neutrons 2,000 times heavier, and the stripes remain. Trade neutrons for Buckminster Fullerene molecules, 60 carbon atoms locked in a geodesic dome, and after a patient night the pattern resurfaces. In laboratories today, researchers plan interference tests with tiny viruses and silica beads containing billions of atoms. The rule is not small equals quantum, large equals classical. The rule is privacy. Keep the environment from eavesdropping, and even a microorganism might sketch two histories at once. Why then do desks stay put and cats decline to blur? Because the world is nosy. Air molecules bump, infrared photons pry, and information about where and when leaks at dizzying speed. The delicate overlap shreds an early hint of decoherence that will shadow our story. Superposition is not just a party trick for physicists in darkened rooms. A quantum computer wields it the way a sailor harnesses wind, letting qubits glide through billions of pathways simultaneously before canceling wrong answers and amplifying the right. In a leaf, sunlight births an excitant that explores every molecular corridor at once, settling on the quickest chute to the plant's chemical engine. Atom interferometers drop down elevator shaft laboratories, split and reunite matter waves to weigh Earth's gravity so precisely that shifting magma flows betray themselves months before a volcano stirs. Indecision, it turns out, can be exquisitely productive. But if a speck of carbon can stand in two places at once, what happens when we wire that quantum coin flip to a vial of poison? And ask a warm-blooded observer with 9 lives to stake its fate on the roll? In the next act, we knock on the lid of Schrodinger's infamous box. It is the spring of 1935. Albert Einstein sits beneath a Princeton elm, still wary of the strange new physics he helped spark. He argues that quantum theory cannot be the last word. Surely the world carries hidden certainties beneath its probabilistic fog. Erwin Schrödinger, pacing a Swiss mountainside, hears the challenge and decides to dramatize it. Fine, he says in essence, let us not speak of ethereal electrons. Let us gamble with a creature of fur and breath. And so the stage is set for the most infamous box in science. Picture an oak chest hardly larger than a wine crate. It seems sealed tight against every stray photon of light. Inside rests a minuscule time bomb of chance, a single radioactive atom destined to decay. But no one can say when. Beside it stands a Geiger counter poised like a sentinel. One faint click will fire an electric relay, tipping a hammer, shattering a fragile vial, and releasing a puff of cyanide gas. Curled in the far corner, oblivious, dozes a healthy black cat. At the stroke of noon, we shut the lid and start the clock. For 1 minute, the interior is utterly private, no peeking, no whispers from the outside world. In that quiet, the atom lives in two possibilities, undecayed and decayed. The Garda tube is both silent and shrill. The hammer hovers and swings. The vial is intact and splintered, and the cat is both purring and gone. The mystery is not the cat's whim, it is the domino line of entanglement. First domino, the atom's quantum uncertainty. Second, the detector wired to its fate. Third, the mechanical hammer. Fourth, the delicate vial. Fifth, a living organism whose every cell breathes or suffocates, depending on the upstream maybes. In a single, seamless wave of possibility, subatomic indecision is amplified into macroscopic life and death. Imagine two ghostly scripts superposed atop one stage set. Actors walk both plots at once, till a spotlight snaps on and forces the troupe to pick one storyline, discarding the other forever. Where shall we place that spotlight? Stand outside the chest, stopwatch in hand. From your vantage, nothing collapses until the lid creaks open. The wave of maybes still hums within. Now climb inside. In thought, safely masked. Your eyes, your ears, your very neurons become part of the entangled machinery. Do you act as the spotlight? Some say yes. The instant you witness the cat, the uncertainty folds. Others retort that the cat's own nervous system is audience enough. Her first breath, or lack of it, writes the ending before we ever arrive. The paradox is not about feline welfare. Is a mirror held to our definition of observation? Does reality wait for consciousness, for a censor, for any irreversible imprint on the environment? The box offers no hint, merely sits, inscrutable and silent. For decades, the thought experiment seemed safely philosophical, till laboratories learned to engineer cat states without whiskers. At Yale, a ring of superconducting aluminum chilled close to absolute zero manages a bizarre feat. Electrical current flows clockwise and counterclockwise at the same moment. Microwave pulses read out the loop, and interference fringes confirm both realities coexistent till the measurement chooses. Across the Atlantic, in a darkened chamber, physicists levitate a silicon nanosphere on a cradle of laser light. They cool its motion until the bead's wave function swells larger than the bead itself, occupying two positions at once like a dancer mid-leap frozen in double exposure. Stray gas molecules, a passing cosmic ray. Even a photon leak can collapse the pose. Yet for precious milliseconds, the paradox lives in glass. No poison, no claws, just quantum mechanics wired to levers we can finally pull. It is tempting to imagine Schrödinger chuckling, conjuring undead cats to antagonize his colleagues. In truth, he sought clarity, not chaos. By scaling micro-uncertainty to macro-absurdity, he forced physicists to confront a contradiction hiding in plain sight. Either the quantum description is incomplete, or our everyday intuition that objects possess definite properties at all times is simply wrong. 80 years on, the box still refuses to declare a victor. We know the math that predicts interference and collapse with stunning accuracy. We wield it in lasers, GPS clocks, and nascent quantum processors. Yet we do not all agree what that math describes when nobody is looking. To decide, we must wander beyond the lid, into interpretations that say reality splits like branching novels, or that a silent mechanism snaps the wave shut the instant information leaks. In Part 3, we will meet these competing stories, weigh their evidence, and ask how a universe built on superposition chooses a single script the moment an observer steps on stage. Imagine standing at the mouth of a cave where two tunnels vanish into darkness. A marble rolls in, splits like mist, explores both passages at once, and, according to every experiment we've ever run, reemerges as a single solid click in a detector. We can predict the odds of left or right with uncanny accuracy, yet we cannot say, in ordinary language, how the marble chose. That final moment, when shimmering possibility shrinks to a single fact, is called measurement. Quantum theory sketches the journey up to the brink, then closes the curtain. What happens behind that fabric? Does a hidden mechanism spin a cosmic roulette wheel? Do parallel theaters each perform a different ending? Does consciousness shine a spotlight that forces a decision? This remains as our most persistent riddle. The equations are a piano. Interpretations are the songs we play upon it. Copenhagen, Niels Bohr, and Werner Heisenberg imagined the quantum wave as a menu of dishes. While we ponder, all are listed. Ordering observing brings one plate to the table, the rest vanish from the chalkboard. The menu is not the meal. Reality solidifies only when served. Hugh Everett proposed the many worlds interpretation. In this restaurant, the waiter delivers every dish to every version of you. A trillion branching rooms bloom each instant. One where you sip tomato soup, another where you savor miso. No collapse, just an ever-dividing ledger of fates. Christopher Fuchs and colleagues suggested QBism. Here the menu lives inside you. The wave isn't an external catalog, but your personal bet on tomorrow's taste. Observation doesn't sculpt the world. It updates your beliefs after every bite, like a weather app refreshing a forecast after new data. Finally, the objective collapse interpretation by Girardi, Rimini, Weber, and later refined by Roger Penrose. In this kitchen, the overhead light flickers randomly. When it blinks, one potential dish crystallizes, the rest evaporate. Collapse is a real, spontaneous event. Tiny 4 atoms, but inevitable and roaring for cats. 4 melodies. 1 keyboard. All reproduce interference fringes, qubit logic gates, and laser diagnostics. Yet each paints reality in a different hue. Step into an empty cathedral and clap. Echoes, bounce, overlap, fade. Now, fill the hall with a bustling crowd dialogue. Footsteps, phones. Clap again, and the echo dies instantly, drowned by copies of itself. Decoherence is that drowning, but in silence so small we cannot hear. Every particle whispers its state to air molecules, stray photons, the thermal jiggle of walls. Those whispers multiply 1 trillion times a second, shredding the fragile phase links that let paths interfere. Nothing explodes, nothing collapses. The quantum script is merely overwritten by environmental gossip faster than any cat could twitch a whisker. The result looks classical, pointer straight arrows. Definite locations not because the quantum play ended, but because too many bootleg copies left the theater before the twist could unfold. Wojciech Zurek pushed the metaphor further. He pictured reality as an information savanna, where only the best communicators thrive. A quantum state that broadcasts a clear, redundant story. The atom is here. The table edge is solid, wins countless environmental messengers. Observers sample different shards of that broadcast, and without conferring, all agree. Objectivity is born not from brute collapse, but from redundancy. The same headlines stamped into photons, phonons, dust grains. Competing states that garbled their message, such as delicate superpositions or tangled phase relations, fail to replicate. They go extinct. What remains is the everyday world. The fittest facts, selected by a ceaseless evolutionary contest, waged in the ultraviolet whisper of sunlight and the thermal hiss of air. You might ask, if the math works, why care which story we tell? Well, because stories steer curiosity. Many worlds nudges cosmologists to ponder universes spawning universes, eternal inflation blossoming like foam across unimaginable breadth. Objective collapse inspires engineers to build kilogram-scale interferometers, hoping a tiny random twitch will reveal nature's built-in tripwire. QBism influences AI researcher treating probabilities as personal investments rather than detached frequencies, changes how machines weigh evidence. Interpretation is a budget proposal to the future. It labels some questions fruitful, others idle. The stakes are not only philosophical, they guide which billion-dollar instrument we build next. The next decade may prune the menu. First, macromolecule interference. Physicists in Vienna are preparing to launch organic compounds the mass of a small virus through a 20-meter vacuum tube. Should interference fringes endure, even objective collapse models must retreat to grander scales. Second, optomechanical collapse tests. Suspended mirrors, each the weight of a grain of sand, will be cooled until their center of mass hums in quantum unison. Penrose predicts gravity itself might snap the superposition. A single unexpected jolt would light the path. Finally, macro space mission proposed for the late 2020s. This experiment will cradle a glass bead inside a quiet Lagrange point spacecraft. Free from Earth's rumble, the bead may glide in a Schrödinger-style double path kilometers long. A yes or no pattern could favor one philosophical camp and retire others before the decade closes. Science rarely settles metaphysics in a signature stroke. Yet the boxes we are building now are larger, colder, quieter than Schrödinger dared imagine. They may tip the scales. Yet interpretation alone does not pay the laboratory electric bill. Engineers have already learned to use superposition without untangling its deepest meaning. In Part 4, we'll leave the cat's closed box and tour the bustling factories of quantum. Tech computers that cancel wrong answers, sensors that weigh Earth's heartbeat, and maybe the humble robin that navigates by night on entangled wings. In a quiet lab, a silver cylinder exhales cold like winter breathing. Across town, a fiber spool glows under a technician's lamp. On a bench top, a chip the size of a thumbnail wears a crown of microwave lines. These aren't props for a magic trick. They're the tools of a new craft, using superposition on purpose. If nature keeps options open, engineers have learned to guide those options, cancel the wrong ones, amplify the right ones, and turn quantum maybes into useful work. A classical computer checks possibilities one after another, patient, tireless, but ultimately single file. A quantum computer sets many routes in motion at once, then choreographs them so bad answers cancel while good answers add together. Think of a maze scene from above. Instead of trying every corridor, we let ripples explore the whole layout. Where ripples meet out of step, the path dims. Where they meet in step, it shines. This is more than a party trick. Search problems become leaner. Certain chemistry tasks, finding the most stable arrangement of electrons in a catalyst, say turn from impossible to plausible. Optimization landscapes that look like mountain ranges under fog suddenly reveal passes you couldn't see before. But there's a catch. Superpositions are skittish. A nudge from the outside world can make delicate drafts collapse too soon. So quantum engineers use error correction, spreading one logical bit of information across many physical qubits. In superconducting devices, they even store a bit in two opposite states of light at once, the so-called cat codes, so that a small disturbance doesn't ruin the message. None of this is free. One sturdy, reliable qubit can demand a crowd of helpers. Where does that leave us? Early processors are already useful as co-pilots. Specialists that hand classical computers better guesses for chemistry, materials, and optimization. The moonshot, general purpose, and fault-tolerant machines will take time, patience, and thousands upon thousands of well-behaved qubits. The promise is real, the road is long. Some quantum problems are so tangled that equations alone give up. The workaround is wonderfully literal. Build a tiny, controllable stand-in, trap ions in neat rows, and make them push and pull like electrons in a crystal. Cool atoms into a calm, laser-made egg crate, and watch them act out the drama of magnetism or superconductivity. Use a programmable photonic circuit to mimic how light and matter flirt inside a solar cell. Rather than brute forcing a solution, we grow the equation and observe the answer. The payoff is practical. Better battery chemistries, cleaner catalysts for green fuels, hints for high-temperature superconductors. Sometimes a model universe is clearer than the math that describes it. When you tame quantum noise, the world whispers secrets. Atom interferometers split a cloud of ultra-cold atoms into two paths and reunite them. A tiny difference in the journey. Gravity a shade stronger here than there shows up as a telltale shift. With these instruments, scientists map hidden caverns, trace water tables under farmland, and listen for the swell and settle of magma beneath volcanoes. Inside a sliver of diamond, NV centers, which are flaws just a few atoms wide, behave like nanoscale compasses. They can read magnetic fields cell by cell, peeking into new materials and even sensing the blush of currents in living tissue. And then there are optical lattice clocks. Imagine an orchestra of identical atoms, each keeping time with a note so pure it drifts a second only over the span of the universe. These clocks promise sturdier GPS, better tests of whether nature's constants really stay constant, and ways to sense tiny changes in Earth's gravitational field, say, as groundwater moves. Even light's own hiss can be shaped. With squeezed light, we quiet the kind of fluctuation that matters and allow its partner to jitter more. This trade lets instruments hear fainter signals than classical physics would permit. The difference between missing a whisper and catching it clearly. Imagine sending a stream of single photons, each set in a particular orientation, as if tiny arrows were flying down a fiber. If no one meddles, those orientations arrive as sent. But if an eavesdropper even looks, the act of looking disturbs them. Errors spike. You know to throw away the key and try again. That is the heart of quantum key distribution. Secrecy guaranteed not by clever math, but by nature's rules. To go long distance, we link short, secure hops into a chain. Quantum repeaters use memories that hold fragile links until the next segment is ready, then stitch them together, entanglement passed hand to hand across a continent. These networks don't beam cat videos faster than light. They do something quieter and more profound. They make tampering obvious. Sometimes you can reveal an object with less light, not more. Send paired beams. One touches the scene, the other stays home. Compare them, and a picture emerges from noise ghost imaging with barely any illumination. In murky water, in smoky air, or over fragile paintings that shouldn't be bathed in brightness, correlation beats brute force. Likewise, using entangled or squeezed light can push imaging beyond classical limits, sharpening edges and reducing the grain in low-dose scans. When photons travel in company, their story carries extra detail. Long before dilution, fridges, and clean rooms, life learned to borrow quantum shortcuts. In photosynthesis, tiny packets of energy fan out through a protein maze, as if testing many routes at once. Subtle interference helps funnel that cargo to the reaction center with remarkable efficiency. Sunlight turned into chemistry with almost no waste. Migratory birds may carry entangled electron pairs in light-sensitive proteins called cryptochromes. Earth's weak magnetic field tilts this delicate balance. The chemistry downstream changes. The bird perceives a faint directional cue, a map written in twilight. And in enzymes, tunneling lets protons or electrons slip through energy barriers rather than climbing over them, speeding reactions at body temperature. Not every proposal survives testing, and debate is healthy. But the pattern is clear. When energy is scarce and timing matters, evolution favors quantum economy. It's tempting to imagine a universal quantum boost, a silver bullet for every hard problem. Nature is stricter than that. Quantum algorithms help where interference can be engineered to cancel the wrong answers. Many tasks simply don't fit that mold. Scaling is hard. Single, reliable, logical qubit can demand dozens or hundreds of physical ones. Keeping thousands in step while guarding them from the noisy world is an immense engineering challenge. Progress is steady, not meteoric. On security, the sky isn't falling, but the horizon is moving. Some of today's public key cryptography will be vulnerable to future quantum attack. The remedy is already known: post-quantum classical algorithms that resist both kinds of computers. For secrets that must last decades, the time to migrate is now. There's also cost and conscience. Big machines mean cryogens, clean rooms, and careful supply chains. As nations invest, we should ask who benefits, how widely training and access are shared, and how to minimize environmental impact. Responsible storytelling matters too. Quantum miracle headlines may harvest clicks, but they plant confusion. Let's celebrate real benchmarks, admit uncertainty, and be honest about timelines. Wonder does not need exaggeration. If superposition can root a maze and measure a mountain's hollows, why doesn't your coffee mug blur across the table? Because the world is a relentless observer. Air molecules, stray light, the table itself, each steals a hint of the mug's state, shredding the delicate phases that make interference possible. Engineers fight this decoherence by carving tiny sanctuaries, brief shelters where quantum drafts can work before the curtain falls. And yet, even inside that curtain, the lesson is generous. We live among many maybes, most of them hidden, some of them harnessed, and build our lives from the few that harden into facts. In the final act, we'll gather the threads. What the cat taught us, what superposition means for meaning itself, and how to carry a little quantum humility into a classical world. We began with a simple riddle. Can one thing be in two places or two fates at once? The double slit said yes, writing stripes from lonely particles. The boxed cat sharpened the question, showing how a single quantum event can cascade into a story big enough to purr. Along the way, we learned a quiet truth. Nature drafts many possibilities, and the world we witness is the one that survives asking. Superposition isn't a party trick. It is the backstage where reality rehearses. Decoherence explains why the show looks solid. Air, light, and heat act as tireless audience, snatching away the delicate phases that let alternatives interfere. Yet for moments, in carefully built sanctuaries, we can hold those phases steady and put them to work. Ripples that sift answers. Clocks that keep time with almost impossible grace. Keys that physics itself protects. Still, honest mysteries remain. What, precisely, is a measurement, an act, a split, a story we update? Do possibilities collapse, branch, or simply change meaning when we learn something new? Where does gravity join this dance? And why do probabilities take the values they do? The interpretations differ, the experiments agree. That, too, is a kind of wonder. So we end where we started, with humility. We live among many maybes and make our lives in the few that harden into facts. To study superposition is to accept that certainty is often a late arrival, and that curiosity is the light we carry until it appears. This is cosmic canvas, where the universe is not only studied, but painted in meaning. Until next time, keep asking, keep looking up, and never stop wondering.